and me. Who said that every wish would be heard and answered when wished on the morning star? Somebody thought of that, and someone believed it. Look what it's done so far. What's so amazing that keeps us stargazing? And what do we think we might see? Someday we'll find it, the rainbow connection, the lovers, the dreamers, and me. All of us under its spell. We know that it's probably magic. Have you been half asleep? And have you heard voices? I've heard them calling my name. Is this the sweet sound that calls the young sailors? The voice might be one and the same. I've heard it too many times to ignore it. It's something that I'm supposed to be. Someday we'll find it, the rainbow connection, the lovers, the dreamers, and me. La da da dee da da do. La da 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 dee da do.
Good morning. Can you all hear me okay? Yeah, thanks, Egwu. Thanks for popping on. Good to see you folks who are here. Hello. Good to have you all from my home studio today. Great to have you. So today, so you'll notice it's mostly Michigan folks today. Okay. The FAMU FSU folks, they have a career fair, so this of course will be recorded for them. But today I wanted to do a review of dynamics and controls. Let's start off with a few announcements first. 1 second. Yeah. So, a little reminder that your homework due tonight. Okay. I've had office hours. Had a couple people show up. Just so you know, my office hours are open to anyone. Regardless of university, I have the office hour open. Hopefully, people not showing up is an indication that you're getting the homework just fine for first homework. That's great. So homework one is due tonight. And I have it up at 11:59 p.m. Okay. But hopefully that's going okay. Hopefully you're all getting the support you need from the TAs and myself. And if you need something else, just let me know. I want to make sure everyone succeeds on this first assignment. Okay? So, all right. Due tonight and today, I want to do a dynamics and controls crash course. Okay, I guess it's a one way to call it. Okay, but I'm going to say a review. This is an interesting class because we're covering the basics of optimization, also with the basics of dynamics and control, and then putting them together. So it's a fair bit of stuff to cover. So, dynamics and controls review. So what we've covered so far are setting up programs, things like linear programs, quadratic programs. By the way, all the lectures are up, and all of the notes from all the previous lectures are up as well in PDF form. And I've also updated the suggested reading list for the next handful of lectures with links to PDFs in the Canvas page, so you can find all that. It's all available for you. Okay. But dynamics and controls review. Okay. So I want to talk, because what we're going to be wanting to control are dynamical systems. And so dynamical systems are governed by differential equations where quantities can evolve over time. Okay. And in this class, we'll be dealing primarily with the ordinary differential equations. Okay. While we talked a lot about partial derivatives in this course, I'm sorry, get out of your way. We can write that down. Okay. All right. While we did a lot of partial derivatives in the prior sections of the class, right? Those are for helping us solve optimization problems. Okay. But the equations that we're going to be using for our differential equations will almost always be ordinary. Okay, well, will always be ordinary. You'll only expect it to do ordinary differential equations. So, and this will cover mechanical systems, pretty much any robotic system for the most part that you're going to want to control. Things might get a little crazy with soft robots, but that's an active field of research. So, in this course, we will focus on purely ordinary differential equations, DPQs. All right. And this is nice because when you have an ordinary differential equation, no matter how complicated it is, no matter how many you have, okay, we can put them into one form that we're going to see a lot. Okay. So for ordinary differential equations, ODEs, or systems of ODEs, we can always write them in first order form. Okay? And by the way, I should be able, so those that are just joining, I should be able to hear you on the headphones. I can see you right there, right in front of me. So feel free to pop in with any questions. Okay. First order form. Okay. Now prepare yourself. I'm going to use the variable x. Okay. Now, where has the letter x been used a lot in this course so far? Anybody? Anybody? Yeah, what specifically, Egwu, on the optimization problems? Decision variable, decision vector, excellent. And I see that in the chat as well, people popping in. Thank you very much. So thank you for those textually and non-textually joining the conversation. We use it as our decision vector of decision variables, right? Let's see. I see someone in the chat asking, should you turn on cameras? If you want to, okay? I can see you if you want to turn them on, but don't feel pressure to do so. You know, sometimes we're in our pajamas in the morning. I get it. I'm the only one that needs to dress up, okay? So this X, though, is going to be different than our decision vector, okay? And that's by convention, all right? That this X here, before I put the dot, is not the decision vector, something we call the state vector. Okay? So just understand the context of what we're talking about. X here is different than the X that we're talking about in other parts of the lectures. Okay? So X dot of t, which t is time, is equal to some function. And and this is now an f that's a different context. This is no longer your cost function f, okay? This is a different f of t x of t. All right? So that's a function. So we call this first order form because it looks like a first order differential equation. You got one dot, that's your, for those who don't know, dx dt is equal to x dot. All right. Second derivative of x with respect to time is x double dot. Each dot is a time derivative, for those who haven't seen that before. Okay? Right. That's first order form. And you can write any ordinary differential equation or system differential equations in first order form, okay? And your ordinary differential equations, those are your dynamics. That's your dynamical system, okay? All right. So there are specific subsets. So note when f is not explicitly a function of time, it is called an autonomous system. So people dealing with all different manner of control systems might have to turn something into an autonomous system first. So it means that x dot of t is equal to f of x of t, right? So there's no t comma, all right? That says, yeah. All right. So question is, so a state vector x, well, it's a vector containing, and they're of t, time varying state variables. Okay. And why are we doing this? Why are we putting something in first order form? Why are we introducing these things called states? We have some differential equation already that defines your system. Okay. And the answer is because you can do a lot in this form. If you put something in the first order form, there are a myriad of tools with which you can simulate the system. Okay. You can simulate it. You can put it into MATLAB or or Julia or any such equivalent language, and then their simulators will often ask for you to give the equations of motion in first order form. Okay, and that's going to be super important for your projects and your upcoming homework. Or I'm going to give you some physical system, and you're going to have to be able to simulate it. Okay, and additionally, when you put it in this form, there are all kinds of cool tricks you can use to control it. All right. And some of the best tricks out there require you put it in this form first. Okay. All right. So you got a state vector filled with state variables. Okay. And a state vector contains the fewest states necessary to represent the ODEs in first order form. Okay? Because basically, you're going to have to choose, when given a differential equation, what goes in this state vector. You're choosing that. Okay? And there's going to be a question of, well, how many states do I need? And what should they be? Okay? I'm going to give you a procedure by which you can determine the number of states and then put in the right states. Okay? I'll give you that procedure. But first, let me lead off with an example of how this would work. With one of the examples we love to talk about in controls a lot, the humble pendulum. Okay? All right, so I'll try not to overuse the pendulum in this course, but, now's a good time. Okay? So, an example. Consider a pendulum under gravity. Okay? So, you got your pendulum is hanging from the ceiling. So you got your pin joint up there, as we mechanical engineers like to call it. You got your rod of length L. Then you have a bob. That's the heavy thing at the bottom of mass M. We'll pretend it's a point mass with no inertia, rotational inertia to it, and it'll be under gravity. And we're going to define our angle theta relative to vertical, and that can change over time. Okay? Hey, look, we have something that evolves over time. It's a dynamical system that we're going to define with an ordinary differential equation. Now, using physics 1 free body diagrams, you could come up with the equation of motion. Your dynamics. Theta double dot of t, which is your second derivative with respect to time, so your angular acceleration, is equal to minus g over L sine of theta of t, right? We've seen this. If you haven't seen it before, welcome. Congratulations, your pendulums. All right, so classic equation here. Now, what you need to, I want to put this in first order form. Okay? So in order to do this, I need to first define my state vector. X. Okay? And in order to define your state vector, you need to know two things. How many states you need, and what goes in it. Okay? So I'm going to use my prior knowledge of this course, and many of you who've seen state space controls before would know how many states this needs. This is going to need 2 states, okay? And that's because, and the short answer is because this is a second order system. There's the theta double dot equal to minus g over L sine theta. So second order system generally means 2 states. It's a little bit more complicated than that. We'll get to that in a minute. But 2 states. I'll call them x1 and x2. Now, they vary with time. I'll try to remember my of t's. Okay? All right. And I'm going to define it in terms of my problem. X1, I'm going to say my first state variable is theta, the angle of my pendulum. I chose that with my brain. We'll do it with a procedure next. And as my second state, I'm going to take the time derivative of that theta. So theta dot of t. Okay. So there's my state vector. X of t is equal to this theta t, theta dot of t. All right. And because I made some decisions with malice aforethought, okay, I know that I'm going to show you how this works out when I put it into first order form. So recall, first order form was x dot of t is equal to f of t x of t. All right, so we need to make the left side a function of t and x of t. So what is x dot of t? Well, x dot of t is the time derivative of x and each of the elements of x. That's how you take the time derivative of a vector. Just take the time derivative of each of the elements. So that means it's going to be x1 dot of t, x2 dot of t, which is equal to the derivative of each of these elements, right? So that's theta dot of t and theta double dot of t. Look at that. Okay? All right. That's sort of the left side. That's the x dot of t. We did that part. But we have to, on the other side, make it equal to some function of t and x of t, which is that's our state vector right there. Okay? So we want to rewrite these in terms of a function of our state variables. Okay? We got our state variables x1, x2, which are equal to theta and theta dot. Okay? So let's look at this top entry here, theta dot of t. Can we write that in relation to any of our states? The answer is yes. Look, x2 equal to theta dot, right there. x2 of t. Now, what about this one right here? Theta double dot, right? Can we write that in terms of our states? The answer is yes, because we have this equation, our dynamics, our ordinary differential equation. Okay? Theta double dot of t is equal to minus g over L sine of theta of t. Is theta of t a state? It is. We set it up that way. It's state number 1, our first state. Okay? So it's minus g over L sine of x1 of t. Okay. Okay. All right. So it's in first order form now. Okay. The derivative of x of t is equal to some function of t and our states. We did it. Good job. Okay. So, but that was dependent upon us setting up the right state vector. Okay. All right. Any questions so far? Before we start, I give you some simple rules for setting up the state vector. Yes. Yeah. So you try to do X and Y as your state. So the reason, so where that would become a problem is because if you would have a hard time getting the right equation. You would have, if someone gave you the right equation that included X and Y, you would theoretically be okay, but it would require adding a constraint, okay? Because this Bob can't move just anywhere in X and Y, right? So that would be a constrained dynamical system. So this doesn't require any, and this is a fantastic question because we talk about constraints in the rest of the class. This would be a slightly different kind of constraint, so I'm kind of avoiding that for the moment. Okay, this is a great question. Great question, right? You could set it up with X and Y as states, but you would also need a physical constraint. Okay, who here, just by show of hands, okay, who here have heard of a Lagrange multiplier? Has anyone heard of this? Anybody? Okay. Okay, some of you have, right? For those who haven't, okay, who here has heard of a reaction force? It's a ground, like a reaction force, like the ground reaction force. It's the thing that keeps us from falling through the ground right now, right? You would have to be able to compute that as well. So hope that answer gives you some context for the question. So, but that's all on the dynamics side, right? Okay, so they would give you the dynamics, and then you have to determine from the dynamics what states you need. Okay. Okay. So I hope that answers the question. Some I over-explained it as usual, but thank you. All right. Okay. All right. You got it. All right. So what can go wrong if you choose the wrong number of states? Well, if you don't choose enough, it's not going to capture the dynamics of your system. If you choose too many, it's possible that you'll do okay. You just added more information than necessary. But it's also possible that you create states that are linearly dependent on each other. And what that creates problems with is that when you're doing math with this cool form, all of a sudden the math that requires matrix inversions, the math that requires you to turn these things into matrices and do calculations, will stop working. Okay, so by using the fewest number of states possible, you avoid that possibility. Okay, all right. So a procedure for building the state vector for ODEs. Okay. Number one, you want to identify each independent time varying quantity. Okay. So that would mean the example that, but I see your email name is Yatin Lin. Is your name Yatin? Yatin. So in the example that you gave, you could choose, if you had in your equation an x of t, and I'm going to call it z of t. Sometimes robotics up is z, if you'll forgive me. All right. I'll use your example. All right. Z of t, That's it. Those are all, these could be different things in your equations that are varied, right? But not x of t and x dot of t. Okay? Because these are dependent, right? You know one, you know the other. Okay. Identify each of those. Number 2, okay? You want to identify the lowest and highest order derivative of each quantity, each independent quantity. So, for instance, if you have x double dot of t, that's order 2. X of t is what order? Anybody? It's order 0. Thank you, Egwu, for giving me the right answer just in time. Thank you. All right. Why is that? Because x double dot of t is d squared x of t dt squared, right? So that's your order. This is d0 x of t dt0, right? And one to note, the integral of x of t dt, that will be order, we count that as order -1. Going in the opposite direction, all right? Who here has heard of a PID controller before? Anybody in their life? Yeah, a lot of you. Very common controller. Oh, look, so many. All right, why am I even teaching this class? Right. So, no, just kidding. But that's, there's the I term of a PID controller takes the integral of some of your states in effect, right? So that means that adding this integral term to your controller may affect the number of states you need in your first order form. Okay? Spoiler ahead. Okay? So identify the lowest and highest order derivative of each independent quantity. There you go. And then number 3, the number of states should equal the sum of all highest order orders minus the sum of all lowest orders. Okay? So if you have 2 independent quantities, so if you had x double dot, and x, so let's say your quantity of x will have like a highest order of 2 and a lowest order of 0, and you had z, which had a highest order of 2 and a lowest order of 0, you would add those two 2's together, gives you 4, minus 0 plus 0, 0. 4 minus 0, mathematicians will tell you, is 4. 4 states. We'll go through an example after I give you the last step. Number 4. Build a state vector including the lowest order derivative each integer higher derivative up until but not including the highest order derivative for each independent quantity. Okay? That's step 4. And that's it. Let's go through an example. Okay. Fun. An example, and I'll just give you an equation. It's for like an arbitrary system. Let's say you got your example system. We'll say that x1. So we'll give 2 different names for this. Okay, apologies. Example. Okay, all right, cool. Let's go for lowercase q double dot of t is equal to r dot of t plus q of t. And I'll add another equation saying r double dot of t is equal to minus q of t. That's my system. So construct a state vector for this system. Okay. So first step, we want to identify all of the independent time-varying quantities. Okay. You know what? I'm going to add another one, just make it a little bit more tricky. Plus u of t. All right, that says u of t. And my glare, I'll try to fix the glare so you can see it. Kind of. All right. My lighting needs a calibration. Sorry. So that says u of t. All right. So first we want to identify all time-varying quantities that are independent. So our time-varying quantities are, in this case, Q, R, and U. So Q of t, R of t, and U of t. Okay. Now, second step, we need our highest and lowest order derivatives So we'll put lowest order for Q and highest order for Q. Anyone want to tell me what the lowest order for Q is for derivatives? Zero. Thank you, Joseph. Thank you. And the highest order? Anybody? It's 2. Thank you. Look, I appreciate. Hey, I applaud you all for. Thank you for participating. Gives me joy on this Tuesday morning. So thank you. All right. Thank you very much, Elena. So 2, right? Okay. Same thing for R. So now let's look at R. Okay. What's our lowest derivative for R? It's actually 1. It's that R dot. There is no R of t, right? 1. And then your second order here, it's 2. And for U, our lowest order is 0. That's U of t. And 0. Okay. Great. Now 3, we want to take the sum of all our highest minus the sum of all our lowest. So that's going to equal sum of our highest is going to be 2, 2, 0 plus 2 plus 0 minus the sum of our lowest, 0, 1, 0. 0 plus 1 plus 0. Mathematicians will tell you that that's equal to 3 states. That's all you need. 3 states to represent that problem. Three states. And then step 4, let's construct the state vector. So x of t is going to have 3 states in it. You can call them x1 of t, x2 of t, x3 of t, three states. Now the way we construct it using the variables that we have is you start with the lowest order derivative and go all the way up to the highest, but not including the highest derivative. So let's start with our lowest derivative of q. So lowest derivative of q is q of t. Okay. Then we go up in order to q dot of t. Q dot of t. We do not include the highest order. We stop at q double dot of t. Not in there. Okay. X3. So we have r dot of t. That's the lowest order of r. So it's r dot of t. And we stop before our highest order derivative of r double dot of t. And u of t doesn't make it in at all because the lowest order is the highest order. So we exclude the highest order, not in there, not a state. Okay, there you go. There's your state vector. And you could use that state vector, like we did in the prior example, to get a first order form of those equations I just erased. Cool. Now, why is that important? Okay. And so for those of you who want to follow along in MATLAB, want to pull open MATLAB, now might be a good time to open that up if you're back at home. And you can follow along with me in a little coding tutorial for how we're going to use this stuff. Okay. And because we're going to want to use it for, first thing is to simulate our systems. Okay. Now, simulation of an ordinary differential equation is just integrating, solving the differential equation, which typically involves integrating, right? And those of you who took differential equations probably had some practice in solving differential equations, certain forms, okay? But some equations cannot be solved. So there is no existing mathematics to give you an exact mathematical solution to many differential equations. So we often have to rely instead on numerical solutions on computers to give us iterative approximations of the solution. Okay, and they will require, many of them, a system in first order form. Okay, but before we get to the computer side, let's talk a little bit about control. Okay, all right, control system. Okay, there are a lot. The control's a big field, and we're gonna jump straight into the parts that are be most relevant for this course. Okay, that there are two major types of control in the Dr. Hubicki school of control. I built it into these two categories. One is called feed forward. And the other is called feedback. And you can do both at the same time, but those are the two major categories. Okay. So consider the dynamical system in first order form. Yeah, any questions? Heard the rustling of a microphone of a curious student. Okay, all right, maybe not. All right, in first order form, where you have x dot of t, which we know to be the derivative of the state vector, is equal to some function of t, x of t, and u of t. Okay, this looks familiar, except this u of t is what we call our control input vector. Okay. That control input vector, our control input, unlike our dynamics, which are what they are, the dynamics that come from the physics or biology or whatever underlying mechanisms of your system are, our control inputs, we get to choose. That's the fundamental difference. That we have a lot more, ironically, control, meaning agency to decide what it can do, irrespective of the physics, okay? So our control are, unlike dynamics, our decisions that are up to the volition of a control designer. Okay. Examples. One is torque to a motor. Okay. Almost all of you are in robotics program. At some point, there's probably a motor involved in the systems you're working with, and there's probably a motor torque or a motor current. So motor torque. That's a current. Okay. Let's say if you're driving a car. So how much you press the accelerator of a car or angle of the wheel. You have some degree of arbitrary control, your ability to change that. A cool example I like to talk about, a very interesting application when I first heard about it in optimal control, is medical choices. Okay, if you are giving someone chemotherapy, you have to decide how much of the chemotherapeutic cocktail you give them in a given session and over what period of time. So medicine dosage. And people have built dynamical systems that model tumor growth. And not just the size of a tumor, but also the size of different populations of cancer cells within a malignant tumor. And so people have come up with all kinds of interesting control systems that use the dynamics of these population growth and decay to the advantage of the treatment, where you might think naively, or at least I naively might think, the solution to the best possible chance you have of saving a patient would be to bombard with as much chemotherapy as you could while keeping the patient alive. But there have been studies that show that if you do that in some cancer cases, what that can do is that can kill off a single population of cancer cells that was competing with other cancer cells and keeping the overall size of the tumor at bay, because this tumor is actually competing for resources for growth. So people have found that people use LQR, linear quadratic regulation, to try to use that understanding of the dynamics of the cancer tumor to keep the tumor from growing out of control. Pretty cool, right? I think that's really neat. So something that you choose. So you can envision your system as a block. Okay? Which has some control input, and some input, and then some output. In a very general sense. And a system where you just send in an input based upon whatever information that we have right now. We say this is going to be our input. Okay, this is our input. It's going to be U of t. Okay, it's going to have some output we'll call Y of t. These are the things we measure. Maybe we measure the tumor growth. Maybe we measure the motor position. Okay, you send in an input, you get an output. We call that feed forward. It just goes forward through the system. Okay, this is a feed forward controller. Okay, and this is what we call a block diagram. You have a system and you have a signal going in, signal going out. If you're a mechanical engineer, you might have taken a course called Controls, where you call this a controls class. You learn this. If you're an electrical engineer, you might have taken a course called Signals and Systems, where you will do this kind of stuff as well. The signals and the systems are here. Okay, that's a feed-forward controller. So, feed-forward controller, the control signal does not depend on the current state x of t or output y of t. Closing it on 10:23. Good 20 minutes left. That'll be enough time for what I want to do. When we get to the MATLAB portion. So, in contrast, we could have our input u of t goes into our system and comes out at some output y of t. Looks familiar so far. But I can take that signal, which is measuring the numbers of the outputs, measuring all what those numbers are, the position of your motor, the size of the tumor, and we can measure that, right? Let's assume we put a sensor on it. We measure it, and I'm going to take this signal and I'm going to feed it back, okay? Another little arrow, which goes into a circle, okay? Has a little X in it. And here, we're going to have another input. We're going to call it R of t, which you can think of as a reference. And this arrow has a little positive sign above it, which indicates it goes into this circle, into this object here, called a summing junction. Summing junction. And this comes in with a negative sign, meaning that this signal comes in positive, and then you subtract whatever this signal is. Okay? And then your signal is somehow is now not just some feed forward signal, okay? It is now dependent upon feedback. So the signal feeds back. So this is called a feedback controller. And this is useful because feedback control can adjust the input u of t depending on the current state or output. You can easily see how that's useful. If I were to have a control system for an oven to preheat to a particular temperature, and I gave it just a feed forward command to my cooking element, said, I want you to be on for exactly 10 minutes. That might, I might have calibrated that 10 minutes so it's perfect so that it shuts off right when it hits 350 degrees, for instance. Okay? But if someone comes along, opens the oven door to check and see what's going on, releases that heat, all of a sudden the temperature is much lower than I hoped it would be. Instead, what you could do is you could measure the temperature as your output, compare it to your reference temperature that I want by saying, hey, I want 350 degrees positive minus where my actual temperature is. Okay. And then I can use that difference to inform my control. Okay. In fact, what people will do is they will put another block in here, little tiny block, if you can fit that in there. All right. They'll call that the controller. So it'll take the difference between your reference and your output. It'll take and that has a particular name as well. The difference between your reference and your output, or R of t minus Y of t, we call E of t. I'm sure someone knows what that is. It's called the error. That's not the red code that MATLAB sends you, in this case. Not the red text, the scary red text. It's the error. It's how far off you are from where you want to be. So it'll take that error signal in, go through some subsystem that we define, call our controller, and spits out a control input. Okay? That's super handy, so you can adjust to the current situation, which makes sense. So that means that for those of you who came into this class with no controls background whatsoever, you might have thought of controls as a bunch of code, a bunch of computer code. And technically that's true, in that we will be implementing these controllers as code, even though you don't have to necessarily. People have made controllers with resistors, the capacitors, because a lot of the time you can make an example controller, very simple controller, where you might say that U of t is equal to some constant k times E of t, where this constant is called a gain. That's a proportional controller. It's a proportional controller. That's the classic one, or the P controller, where this gain is a constant. And who gets to choose that constant? We do, the control designers, okay? And how we choose that constant changes how the system behaves. This is a very simple controller you can use for a lot of stuff. Additionally, you could have a different k, we'll call it kp, times E of t plus kd times E dot of t, where this is a proportional gain. This is called a derivative, so this is proportional gain that we choose. There's a derivative gain that we choose. Basically, it adds a term that's proportional to the derivative of our error. Okay, this is actually a good tool for slowing down our system. Okay, this is called a PD controller, proportional derivative controller. And those of you who've seen any of this before know where I'm going next. You can have a PID controller. U of t is equal to Kp E of t plus Ki, the integral, times the integral of E of t dt plus Kd E dot of t. This is your integral gain. Who gets to choose that? We get to choose that. So this is a PID controller. Okay. All right. Now, each of these controllers have different properties that you could take a whole controls course on for showing how they work. And also, you might be asking, we get to choose these controllers, we get to choose these gains. How do we choose these gains? Because how you choose them can make your system behave really well or go unstable. It could or be horrible. Okay, you can make a Segway that drives around with these controllers, and my Segway. Okay. Right, and you choose the wrong gains, they can flop on your face. Right. Okay. So one of the techniques that we will cover in this course will be how to choose these gains like this, optimally. Okay? In fact, a classic multivariable controller is U of t, your control inputs, vector, you can have multiple inputs, is equal to capital K times, minus capital K times x of t. X of t is what in this lecture? It's our state vector, right? So if this is a vector, that's our input vector. Here's our state vector. And here, this is a gain matrix. It's a matrix of those constants. Okay? And there are lots of ways in modern control theory to come up with the right matrix for your system, assuming that your system is linear, for instance, linear time invariant. Okay, we haven't gotten to that yet, but just a little preview. You could use something called LQR, which is going to be in our class, which you create a cost function, okay, for your problem. You want to make your cost function be some combination of, I want to get my Segway scooter to be upright and also move at the speed I want. Okay, that could be your cost function that you want to get as close to that state as possible. Also, while not using too much motor torque to drain the battery, right? You can create a cost function like that, and LQR will give you the gain matrix. Okay? So if you came into this course thinking the controllers were if-then statements, they can have if-then statements, that's fine. But a lot of control theory and the best stuff that we come up with is often these equations for controllers. So with the time that we have left, which is very little, okay, I want to use what we've learned to go into MATLAB and go through an example. Is that cool by you all? Kind of we might go a little fast through it, so I apologize. Okay. My podcast mic. Hello. Welcome to my podcast. All right. So, all right, we have here MATLAB. Everyone sees it? Say hello. Yeah. And this is being recorded in higher quality in case there's any kind of pixelation. This should be much more straightforward than uploading the other videos. So you should be able to get the high 1080p recording up pretty shortly. So, all right. So we can make, what we're going to do is we're going to simulate that pendulum we put at the beginning. Really low quality at the moment. Okay. Well, I'll tell you what I can do. I can make it a little bigger. Let's go. It'll be a little bit comical. So 32, I'll make it bold so it's easier to see. Yeah. Unfortunately, because it's not a formal screen share, it gets a little bit potato quality, but hopefully you can read what this says. It says 1 + 1 is 2. Okay. So what we're going to do is we're going to make a quick simulation of a pendulum. So I'm going to create a new script up here. Thank you, Aaron. I appreciate the feedback. Okay, and it will be better quality on my local recording. So we're going to make a new script. I'm going to call it StimPend. Okay, StimPend. And the first thing I like to do, I got to remember to do this, put my name at the top of my paper. There's so much code I haven't put my name on. I'm going to clear the screen. I'm going to clear all the variables. I'm going to close all the plots. Love to do those three things right at the top. Okay. Now I want to simulate my pendulum. So I'm going to declare some parameters for my pendulum. I'm going to use the equations I put on the board before. Okay. Which is on the screen right now. But so I'm going to declare my mass, even though we don't need to know the mass for a pendulum, is 1. I'm going to say that our G is 9.81. 9.8. Let's go with 9.8. Make my L is 1 meter. That's meter. That's meter per second squared. This is in kilograms, but it doesn't matter because the equations of pendulum motion of a pendulum without gravity, without air resistance, there is the mass does not matter. Okay. So what we're going to use, what we're going to do is we're going to try to simulate this pendulum system using a command in MATLAB called ODE 45. Okay. Now we'll cover in another lecture how to do some more different kinds of numerical integration, but this is a way to numerically integrate solve our differential equation, point to point to point to point. You give it an initial condition, it'll estimate the derivatives, step forward, step forward, step forward. Okay. You have to do that because it is literally impossible to solve the differential equation governing a pendulum. Okay. So we have to do it numerically. All right, so a pendulum under gravity, to be specific. It's impossible to solve. So how does ODE 45 work? If you ever need to know how to use a command in MATLAB, you could go to MathWorks online, or you can type help ODE 45. And the 45 stands for uses a 4th and 5th order Runge-Kutta integration scheme. Okay, so solves. It's a great solver. Solves a non-stiff differential equation. It's a medium order method. It should be your first go-to for just solving a differential equation. Okay, what does it take in? It takes in an ODE function. Okay, that's the trickiest part. The time span you want it to simulate for, and the initial state of your system. Okay, so recall our state. It was going to be theta and d and a theta dot. So I'll call it d theta and transpose. Okay, that's our state vector. All right, so that's going to be what our state vector was, just to recall. Okay, so what we need, what does this ODE function do? Okay, the ODE function is a function handle. Okay, and we covered this, I believe, in my MATLAB tutorial, where it takes in the current time and the current state and returns the derivative, the time derivative of both of those states. Okay, that means, so I'm going to create a function. I'm going to call it ODE fun. It's equal to at open parenthesis t and y. Okay, this is me defining a function in line. Okay, you could also make a new function file for those who've done that before. You can do the same thing, but this is really simple this way. Okay, where it takes in y, which is going to be a state vector. How many states do we have? 2. Okay, and you'll recall that our derivative of our first state, if you check back in your notes, was so your first state was theta, so the derivative of it was d theta, which is your second state. So we would say we want to return a vector where the first element is our second state. Okay. Then we want to move down, so we hit semicolon. We want to move down to the next element of the vector, and we want to return the derivative of our second state. Our second state was d theta, so the derivative of it was theta double dot, so the acceleration. So theta double dot was equal to minus g over L times sine of theta. And theta is our first state. So y1. So we index. So y1 has our first state. Y2 is our second state. Okay. I have defined ODE fun. Okay. You could do that in a function file just as easily, but this is really clean and easy to do this way. So now I need to define what else? My t-span. I'm going to simulate my system for 10 seconds. So you can say I want my time to span between 0 and 10. And I put that in a little row vector like that. My y0, which is my initial state, where do we want our pendulum to start? Okay. Vertical 0 is vertical hanging down. So let's start at 45 degrees, which we're using sine, but not sine degrees. So we have to give our angle in radians. So that's pi over, so 45 degrees is pi over 4 radians. So that's our first state. So our first state is pi over 4. I put it in a little vector. And our second state, I'll have it start at 0, meaning that our d theta, or our angular velocity, is 0. This is our initial state. This is our time span. All right. Okay, now we want to use ODE 45. So it returns a vector called t out, which are all the time steps that it's plotting, and y out, which is all the states over time. Okay, where the first column is the first state over time, and the second column is the second state over time. I kind of did the opposite, but you know what I'm doing. Okay, equals ODE 45. We want to give it our function handle, ODE fun. Okay. We want to give it our time span, t span, and our y0, semicolon. Make sure that runs. Okay, it runs. I hit F5 to run it. And the last thing I want to do is plot my trajectory over time. So I want to plot my angle over time. So I'm going to use plot. I'm going to plot time, my time vector, and I want to plot all of my angles. Now, which state is my angle? The first or second? Thank you very much, Egwu. So it's the first, that means it's going to be the first column of y out. If you want the entire first column of y out, we do open parenthesis. I want every row, so colon, but only the first column, so comma 1. Okay. Then comma space. I want it to be a black line, so that's k dash. I'm going to label it because I'm going to be a good scientist today, and we are almost done. I'm going to use the xlabel command. I'm going to say this is time in seconds. And then my y label, which is going to be our angle in radians. I'm going to run it. And then I get this fun little plot. Look at that. It's our swinging pendulum. What do we have to do? We just have to put it in first order form. And now we simulate it, no problem. So there is your rapid introduction to dynamics and controls. And I'll add one more fun thing. Okay. If you want to stay an extra minute, if not, it's recorded. You can see it there before and after. Okay. I can now add, if I wanted to, a control input to the system, a torque. Okay. And so what I'm going to do is I'm going to take this function. I'm going to copy it and comment it out and make a new version. I'm going to add a torque to it. So the way I do this is I add to the acceleration term, I'm going to add some variable called tau divided by the inertia, which is quantity m times L squared. Okay. So if I define a torque up above, if I want to apply 1 Newton meter of torque, I can rerun my system. You probably won't see much of a difference here. It's a very little torque, but you'll notice that it kind of pushes the system up a little higher in radians, then it goes lower down to 0.6, which you can't really see on the zoom version of this. But we can make the torque larger at 10. and then I run it, you can see our angle starts to go like this. What's happening? I applied enough of a torque that it's starting to spin up my system. The angle in radians just keeps going up, right? Or, would this count as a feedback torque or a feed forward? So was it count as a feed forward controller or a feedback controller? Anybody? Feed forward, right? Because it's just a number. It's not dependent upon state at all. Okay. So I could do that. So this is a feed forward. If you have to go, I appreciate it. This is more maybe bonus material. I'm going to create a feedback controller by copying this, and I'll put all this code up online. Okay. So here's our feedback controller, where instead of a tau, I'm going to create a feedback controller, which I'm going to take I want to compare my current angle y1 and subtract it from my desired angle, which will be up. Maybe I want to balance my pendulum, and up is going to be pi radians. So it would be pi minus y1. All right. But I'm going to multiply it. So this is going to be a proportional controller. I'm going to give it a gain of 10. Okay. And I run it, and it does this. And you'll notice that the angle goes up past pi and then back again. It's doing this. It's waving at you. Hello. Hi, I'm Christian Ubicki. It's nice to meet you. I'm a pendulum with a proportional controller. Okay? I added a proportional controller. I can also add to this the derivative controller, which I'll add right now. This will be a little fast. I apologize. So I'm going to add a derivative term. So plus 2 times 0 minus y2. Basically, it's the derivative of my state, my position. I want to take the derivative of that position, which is y2, which is our angular velocity. And I'm going to adding a term that is proportional to that error. And then I run it. And voila, look at this. It swings up, goes a little past, and it comes back to about 3.1. It's coming back to 3.14159. All right. I made a feedback controller really quickly. Thank you all. I'll leave this code up so in case you want to stick around and put that code in there for yourself before we're done. Thank you all for your time. Happy to take some questions.